Hello, our names are Jack, Thomas, and Vincent. This semester, we continued the Mast Collector project, which our freshman team initiated in the fall 2018 semester. This project was first presented to the fall team by Sarah Childs, who is a researcher at the Duke Forest. Sarah asked the team to design a device which would first collect falling masts, including acorns, hickory nuts, and beech nuts. It would then have to separate them from other organic debris, and then sort the nuts by genus. Under the guidance of Dr. Ann Satterbeck and our client Sarah Childs, we identified the shortcomings of last semester's design, which addressed the debris removal aspect. Mast and other debris would first fall onto the upper ramp, which would then funnel them onto the curved ramp. Due to their spherical nature, Mast would accelerate down this ramp and would launch off of it into a small basket. Meanwhile, other debris would not be fast enough to make it into the basket and would instead fall into a small hole in front of the basket. This design was effective at removing debris such as sticks and leaves, but was very heavy and had low portability. Under the guidance of Dr. Satterbeck and Sarah Childs, the team this semester improved the weight and portability of the device.
To address both of these problems while maintaining the original sorting concept, the team decided to make various modifications to the device. Last semester, the team realized that while pressurized wood is durable and weather resistant, it is very heavy. Thus, we decided to remake the box for the mast collector out of polycarbonate sheets, as they are much lighter but still very durable. To fasten the sheets together, we bolted 3D printed joints to the walls because they are easy to replicate. We also used steel L brackets to hold the polycarbonate sheets together to improve the strength of the device. We also used the same aluminum material for both ramps because aluminum is low friction and should not significantly dampen the mast's kinetic energy. To secure the upper ramp in place, we bolted it to the L brackets, which we bolted to the walls. To secure the lower ramp, we again used L brackets to both secure it to the walls and maintain its shape. We also decided to make the device smaller so that it would be less bulky and therefore easier to carry. To do this, we scaled down the size of each component of the device. The dimensions of the box and of the mast collector are 12 by 36 by 24 inches. The dimensions of the top metal sheet are 27.5 by 12 inches, and the dimensions of the curved lower ramp are 24 by 12 inches. We decided to preserve the ramp angles experimentally determined last semester, so we adjusted dimensions accordingly, preserving these ratios. Because the device is smaller, we also had to make the basket for the mast smaller. We made it out of polycarbonate and wire mesh, as these materials are strong and the holes in the wire mesh prevent the mast from decaying. The dimensions of the basket are 12 by 10 by 4 inches. This is to ensure that the basket occupies all of the space inside the collector which mast may fall into.
As we prototyped, however, we realized that because of the device's reduced size, there was a greater risk that large sticks would clog the device. As a result, we decided to construct an upper sorter out of PVC and a sloped net that would catch and remove the large sticks before they could enter the collector. We decided on this design because although testing showed that sticks sometimes collected on the net instead of falling off, no large sticks would enter the collector and almost all mass would still go through the net successfully. We decided to use PVC because it is stiff, durable, and it also stays together well. We also used a cargo net so that it could be stretched to our desired dimensions. The dimensions of the PVC frame are approximately 30.5 by 11 by 6 inches, and it was dimensioned to cover the area over the collector. The net is elevated by 10 inches at its center point, which is the maximum height the net could be stretched. The optimal height of the frame was ascertained through testing and was positioned about 4 inches above the upper PVC joint. Finally, we decided to use a tarp to collect falling mass from as large of an area as possible. For testing, we used a 6 by 8 foot tarp. The tarp will be tied to surrounding trees and will funnel mass into an opening in the middle where the collector will be. To further increase the device's portability, we made the entire device modular by allowing the user to remove the upper PVC frame from the bottom collector. These two parts are integrated via holes in the upper 3D printed joints to secure the PVC rods of the upper collector. Furthermore, the basket is also a removable part and can be slid under the front wall to collect mast.
In this video, you can see our device in action. As you can see, when large sticks are dropped onto the net, they are not collected. Meanwhile, masts both make it through the upper net and land on the upper collector ramp. Then they accelerate down the curved ramp and are able to land in the basket. Meanwhile, leaves and small sticks either they get caught on the net or do not accelerate enough to make it into the basket. After the masts are collected, the basket can be easily removed.
For this iteration of the project, we used the same design criteria as last semester's team, but adjusted the weight of the design criteria to place more emphasis on lightweight and easy to set up, which encompasses portability. Our design criteria were durability, low maintenance, low cost, easy to set up, lightweight, sorting accuracy, and collection accuracy. Because the collector did not sustain any damage from water testing, and when large sticks were dropped on it, we determined that the device met the durability criterion for greater than 3 months of functionality without critical failure. We also determined that the device met the low maintenance criterion for at least 2 weeks with no required maintenance, because although sticks collected on the net, Mast still made it through the net, so the device continued functioning. Furthermore, the combined cost of the materials was less than $500, so the low cost criterion was met. Now that the device is portable and lightweight, the easy to set up criterion of less than 30 minutes for 2-person setup was met. Finally, the sorting accuracy and collection accuracy criteria are not yet met, unfortunately, as the device needs further refinements in order to perform as intended.
To improve the accuracy of the device, we need to readjust the 3D printed pieces that direct mast away from the bolts on the sorting ramp. We also need to lower the height of the basket so that more mast are collected. Once our device can isolate mast from organic debris, the next step will be to add a sorting mechanism to separate the mast by genus. The task of adding this mechanism will be given to a group of freshman engineers at Duke next fall. Once this is complete, the device will be tested and will hopefully be deployed in the Duke forest.